We are a team leading the development of an Internet of Things system capable of detect harmful concentrations of CO2 on the environment. With the application of data collection through MQTT communications protocols with our microcontroller and the server. With its design, we're pointing for an implementation practical for a house CO2 detector and classroom monitoring to prevent ideal environment for disease spread. On the stage of design, we rely on the Altium Designer software to develop our schematic and PCB models. With this program, we had to create our own component designs and footprints, granting us with the opportunity for more control and personalization potential for the PCB arrangement of the system. Next slide, please. To step into our schematic design, I will give a brief explanation about power supply block for our system. Here we have the AC to DC section. With it, we have the option to connect our system directly for the wall sockets. With it, a fuse is crucial to prevent any damages caused by voltage spikes. With the capacitor, we control the signal that is being received by removing any noise produced by deviation on the voltage. Then, with the power module, we will convert the 220 volts of the alternate current to supplying 5 volts to the system. At last, the Schottky diode provides lower voltage drop across the diode at low reverse bias, giving us a safe 5 volt of direct current, making it safe for our microcontroller, the ESP32, and the sensors. And also we implement an emergency supply option in case our system gets out of energy from the power grid. We added a 2-pin GST connector to attach a battery. Next slide, please. Then we jump into our processing layer. As I said before, our microcontroller, it is an ESP32. We supply it with 5 volts through the power grid, or if needed, a battery. In general, we'll be using this microcontroller, the USB, to manage all of our inputs, processing it inside the microcontroller, and then using this to connect with our server to stretch all of this data.
LoRaWAN communication protocol is a low-power wide-area networking protocol built on top of LoRa radio modulation techniques. It wirelessly connects two devices to the internet, and the difference between LoRa and Wi-Fi is that Wi-Fi connects billions of personal and professional devices in homes, businesses, offices, while LoRaWAN is used mainly for home security and access controls. LoRa can transmit up to 5 kilometers in cities and 15 kilometers in rural areas. In this specific system, we are using a LoRa RF M95CW 915 MHz. It uses an LCC package, and this IC is connected through our ESP32 by the use of multiple digital inputs and outputs. It is powered by 3.3 voltage, and it uses an antenna of 15 centimeters that gives it its 915 megahertz capacity. This will help us to send information through long distances through multiple devices across a given area. We also have a sensing and actuation layer. The sensing actually uses a CO2 sensor, an MQ135. It is powered by 5 volts and is connected to the A0 pin of the ESP32. It uses a GLC connector, and also it has an OLED display that is also using the same connector. This uses the TX and RX pins of our ESP32. We also have a buzzer that will send a signal when a threshold is passed. In this case, the threshold is 1000 ppm, and after that threshold is passed, it will buzz and send a sound signal. We also have a relay connected to our ESP32, and when that signal is sent through by passing that 1000 ppm limit, it will activate the relay, and this is connected through a motor. It could be air conditioning, it could be opening window system, and all of that is used to regulate the ppm inside a given room.
Okay, the next part we're going to talk about the MQTT communication protocol. This is a Internet of Things simple protocol in which multiple devices connect to a single MQTT broker or a central server, and these devices can interact with each other by sending or retrieving information. This action is called publish or subscribe. If a sensor publishes information, it means that it sends the data to the client. And if a device subscribes to that topic, they can retrieve that data and analyze it in another location. Next slide, please. Here we are presenting the result of our first test. We are analyzing the CO2 concentration in parts per million. As we can here see, there's a small table or a small points that describe how the concentration affects or how the levels of concentration should be in a space. A normal atmospheric CO levels are 400 ppm, and average indoor CO2 levels are from 350 to 450 ppm, and the maximum acceptable CO2 levels is 1000 ppm. So using this data, we design a code in which when we surpass the 1000 ppm, we trigger a relay that will trigger a motor or will open the windows so air can flow inside the room. As we can see here see, we have three measures. In the first one, we have the normal level is the lowest one, 400 ppm, and we can see that the relay is off. Then we try to enclose the space, but we still have normal levels or acceptable levels. But once we reach 1000, we then immediately trigger the relay, so we can lower the concentration of CO2 in that space. Okay, next one, please.
So we finally have our final PCB design and its operation. This PCB is 100 millimeters height and 100 millimeters wide. You can see how the sections explained before, or the layers explained before, are divided for us to route every component on the PCB. We have the AC to DC section in the upper part, and the battery on the left part, and the relay as well. All of our headers or GST connectors are on the edges of the PCB for a better accessibility. You can see as well that ESP is pretty much in the middle because it's the main microcontroller that will be controlling all the sensors and actuators. Another aspect to mention about the design and operation of the PCB is that we added some polygons to some specific areas where the current is very high, and these areas just involve the AC parts and the relay part, where it is where the high levels of current are flowing. The rest of the tracks are of 0.5 millimeters wide, and that's pretty much how we design the PCB and how it operates. That would be it for the IoT system based on MQTT communication protocols. And now we are going to show some of our first suggestions for 3D case for PCB. As you can see in the images, we first thought of a chimney, an industrial chimney, as our expectation. And well, we thought of dividing the case to be open. We divided a upper part and a bottom part. We made the holes and the spaces for the display and the sensor, and some of cuts to place wires to the entire circuit, which will be inside the case. These are our finished designs, and we will be looking forward to implement them in the future. Thank you.